Good morning everybody, my name is Marco Walter Bassignana and today I'm talking about RPE, which is Robox Path Executor. If we open the RDE, Robox Development Environment, and we go in the Documentation tab, we may go here in the firmware and see the RPE plugin manual. Here we may have a brief introduction about what RPE is. Normally, we use RDE programming language and we just load our program in our Robox controller in order to control a machine. But using RPE we have a higher level programming style. So, despite on the other times we are not going to write a rule and a task, but just a task. This is because the RPE itself is going to make its own rule and its own changes among modes. Here we can take a look at the finite state machine of the RPE. Here the op mode, which is the operating mode variable of RPE instance, is going to go from deactivated at first, then missing power, and then while getting on power it will just check if the zero is being done or not on all the axes of the power set and related to the current axis group. If they are, we are going to manual or execution or passive. Otherwise we are going to make a manual without zeros or to make the homing. Here there is a state of wait homing in order to stay here and do some preliminary operations before going to state 5, which is the homing itself. Many things can be set directly in the RPE. Many things, such as the fast stop, are already handled by this system, and we just need to program in a higher level way just to check, just to deal with motion and to the status of the robot. Now, let's go to our job. But first let's take a look at the video. Here we can see a 6-axis anthropomorphous robot. This is making a demo made by us here in Robox, playing the game of the Hanoi Tower. In this game it has to move the tower from one point to the other, while it is always forbidden to put a big place over a smaller one. For this reason, the robot must move one piece at a time and always move the smallest piece over bigger ones. In order to do this, we can just make a little solver function in our task and then just call the motions we need to do. The motion of the robot can be of two types. Can be joint motion or Cartesian motion. The joint motion are the ones that just request a begin point and a final point, and the system will just move all the joints of the axis group in order to reach that point, while a Cartesian movement is like a row in the space connecting two points, the origin point and the target point. This means that the path will be a line. Of course, since the joint motion will always be possible because every motor will move along and not caring about the others also not caring about the trajectory of all the system, a Cartesian movement may be a little more problematic since it can go through some singularity or through some not allowed points. Now, after this video, let's go back to RD and let's begin to program in RPE. Let's keep the manual here, and now let's make a workspace and a new one. Here we just make RPE lesson 2023 November 23rd. Yeah, I'd like a specific folder and we can create it. Now, let's move the documentation here below so we have the workspace. Now let's make a new RTE project. And here, as you know, here we can have the main configuration of the system, while we have the Fieldbus, settings, and we can use axes. For our project, let's make 4 axes that will be the ones used by our robot. Let's make axis 01, Fieldbus, transducers, let's say ethercat canope, ethercat coe, alright, And let's say Sam and Cam only after 0 cycle. These are the same things we have already done in the course of R3 language. You may see the videos of RDE and R3 to learn more about that kind of things and about the basics of Robox programming. Now let's just copy and let's make more axes. That's number 3. And finally here we have number 4. Now let's go to settings and just do the connection that I still need to do and check the configuration. We don't need this. R3 okay, ladder no need. XPL is the extended programming language that now is something we are not going to use. Further videos will be done to explain this. IP address, miscellaneous, we don't need this stuff. Hardware, OPC UA, no. Fieldbus, general, can open Ethercat DF1 and Modbus. Take out everything, we just want to make simulation. Let's also open programs and Flash. Okay, then let's add a folder which is the F8 used by system files. And now, as we already done, let's go to the configuration to the hardware file and let's choose the F8 folder in order to save that file. As we can see here, the rhw.cfg file will be stored in the F8 folder and no more in the FA, which is the system, let's say system and also user folder, where we would like to put the files related to the structure of our system, but also the tasks that we are going to write in the program tab here. But this is something we're going to do later. Now let's go back here and let's make more settings. Here we have Ethercat, but I think we are not going to use it. General, okay. Here we have system language, let's choose English. Storage, retentiveness, alarms. As you know, here we can see the user and system files. Let's just choose the English file from the RD. So I have to go to C, Robox, RD64, 355.1, etc. And now let's see the RTE. Here, alarm system. And here I can choose the alarm system US. Alright. Then we are going to do our user alarms if necessary. For the ladder part we have nothing interesting, and okay, and that's done. Global variables, now we have no ones. Hardware. I play today with an RP2 Robox controller, so I choose it. And here I see the settings that are good. Finally, the IP network. I enable the BCC communication and I check on ATH3 and I will write my address 10.0.33.1 and of course the network mask 255, 255, 255 and 0. Alright, let's save. It will give me some constraints of the RD version. As we know, I will accept and save it. Now let's make a connection, and again I need to text here 10.0.33.1 and here it's the IP address of the RP2 I would like to connect, and now I can connect to my TCP IP connection. Very well, now we see that the project goes under this connection and it's no more offline. Now we can add a shell, but as you know we can import something we already did before. So let's go to Home, I'll just go up, I'll go to Common Material, and here in the panels of RDE I have my own shell. Alright, and here is the shell, I'll just move it away. It could be smaller, it could just need a little space. Now let's go back to configuration and let's make a power set. Right click, new and power set. Here I'll give a name PS1 and that's my robot power set. I energize with alarm not belonging to my power set and with warnings. And then I set, here we have half a second to make the stop due to delay, due to alarm or due to lack of feedback. In that case, remember, these times we are not going to write the rules of fast stop because RPE will handle all of these automatically. The request will always be my loved register, volatile integer register 10.0. We stay true on the edge. And let's keep the power for half second in order to give time to all the drives to correctly power on and give me back the feedback. And now let's go to enables. And here I'm going to enable the can open or COE. And here is Fieldbus enable. After this, you can go and make the feedback. And again, the main feedback we need is the Fieldbus feedback. Very well. Let's also use my loved R software feedback, which is register 10.1. In this case, we have it easy to just press it with a button and make it go to 0 in order to take out the power from the robot. Then axis, and here we need to add axis, all the ones. Axis 1. Alright. And now the others. Here is number 2. Let's always check all of these tabs. Normally, this is the way I'd like to configure this. But in case, you may choose to do different things according to your network connection, according to the kind of machine you are doing, and of course, according to what you think it's more important or less important and negligible. So here, I add all the ones, and as always, I like this to have all the diagnostic possible. If it is available, I want it. It's better to have some useless messages than not having some very important ones and not being able to understand the situation. Let's save again. Let's click here on the envelope to have the possibility to read messages. And now right click and try to generate all. It says I still have an error, and yeah, of course, they say I have nothing in the AX. Transducer is requested, but we have an associated no node. Alright, let's make a fake ethercut. So we do File, New File. Here I should go to the folder, and let's make an FBC. And so I want to give it the 4-axis. Yeah, 4-axis FBC. Create. Now, while the editor is opening, let's talk about our structure. Up to now, we still have 4 axes and 1 power set dealing them. This is the same structure we already did for the normal R3 programming language style. The difference from this to the RPE style is that later we are going to add, right-click, New, a set of axes. This set of axes is what is going to make the robot. Let's call it robot. The description is the axis group AG controlling SCARA robot, AG off SCARA robot. Let's make it shorter. And now I have to choose a power set. The axis group is related to a power set, and it will automatically link to all the axes listed in the power set. This means we are not allowed to make an axis group with the axis we want, but we must always deal with the power set. This is because RPE is automatically controlling the power set, giving the orders the power on and power off. So we need to tell it what is the power set it has to rule over, and so for this reason we are not going to write any kind of command about this inside our task. Now the starting mode will be, for example, manual without zero cycle. The execution type will be before the rules, because as we said before, RPE is not using rules, but it has its own one. But in case we also have other axes controlled by a rule in RSOL language, we may would like RPE to be executed either before or after the rules. So we may choose it, according to the fact that it could be, for example, a master and do something necessary for other axes, or maybe it will need some information coming from other axes and so it will be executed after the rules. Let's say before the rules. And the fast stop time, again, here we see, let's choose 0.45. That's because the power set timeout due to alarm or lack of feedback in order to cut the power is half a second. In this way, with 0.45, the fast stop time will be already handled in order to be fast enough to stop the axis before 0.5. So, let's go to motor joint. Here, we are talking about our 4 axes. Our 4 axes are 4 motors, and the motors must be connected to the joints of the robot. And as we know, this could be something different from a linear structure. So, for example, we may have a standard situation where every motor is one joint, from M1 dealing J1 to M number n dealing with J number n. But sometimes we may have something more complex. Imagine like a bridge crane, like a gantry. In that case we have 2 motors, the left and the right, both moving the same joint. This means that these 2 motors will be handled by the RP in order to move in the same way, because this joint is a unique one, and so this is a rigid body. The third one could be a cross structure. The cross structure is something used by some robots making some very fast Cartesian movements. Some pick-and-placers may use the cross structure. Otherwise, we may have other strange ones, or otherwise we have the linear parametric. In case you have a very strange and original situation where you have a complex structure of your motors and a complex way to deal with the joints, you may just write your own linear parametric matrix, and in this way you are going to be able to control any kind of mechanical structure. Now let's go back, and since in our case it's just a normal situation of a SCARA robot, they are just one motor per every joint. Here below, according to the kind of joints, we may set some very important things, such as lower end of stroke or upper end of stroke. So, according to this, let's first go to see the other part. Here I want a SCARA robot, and here we can see all the models between joint and Cartesian. So, every joint could be doing different things inside the structure of a robot. According to the conversion, you see we have motor to joint and joint to Cartesian. So now we have old anthropomorphous, Cartesian model, Cobot, the cooperative robot. We have some customized structure used by some important, let's say, some people requesting this and asking us to develop this kind of models. So if you have your own model and that's something special and you do not want always to feed the linear parametric matrix, you may just ask us to develop it for you. Finally, here we have cylindric robot, delta robot, another kind of delta, rotating table, and here we start with a SCARA. Today we have 4 axes, and so we are going to make a SCARA with X, Y, and Z and W. Here we are going to have J1, J2, and J4 doing the rotating axis, while J3 will be the Z axis moving up and down. Now that we have this kind of description, we can easily understand which joint is moving which part of the robot. So J1 is the rotation of the shoulder. Let's go back, and here let's say that the minimum stroke and maximum stroke could be something like plus or minus 120 degrees. Oh, sorry, this is lower and this is upper, so. Then we can set a maximum speed made by the joint. In this case, the joint speed could be the speed of this kind of motor, since the motor is moving this joint. So, for example, let's just invent some number. Let's put even too much, 1000. And maximum acceleration, okay, let's put 1g, little acceleration. If I don't click the maximum deceleration, it will be the same. And finally the jerk. Normally jerk could be such a big number. The jerk, as you know, is the derivative of the acceleration, as you can see from the unit, expressed in unit divided second cube. Here it's a physical value, and for example, for some kind of robot I'm used to deal with, the value is 420,000. Now, let's go to the manual speed. Here, as you see, since we are not going to write the manual rule, all of the data are already requested here in the RPE configuration, in the axis group configuration. So my manual speed will be 50 millimeters by second with an acceleration of 500, a deceleration of 500, and a jerk that could be, for example, 2500 to have a very smooth S style of shape, trapezoidal shape with a S ramp. This will be nice. And finally here, in the zero cycle, we can set how we want the zero cycle of that kind of joint. Here, for example, we just say the zero will be done on current position. Here we can choose, you see, many things. Defined by user, zero channel, zero micro, which is normally the ones used while going and touch a micro. Or then there are end of torque mechanically in order to see the torque reduction and other things. But mainly on robots, the zero cycle is done on current position, so you have to move the robot by hand using jog commands in order to reach the position you want, and finally set a prequote. For example, for this axis we are going to 0 and just set it 0 degrees. We may also have some settings. And here we have the execution sequence. Sometimes some axes are requested to move first and some others to move second or third. Here you may do the order you want, going from number 1 to infinite. Here you can choose every joint which order will have to follow during the zero cycle procedure. If more joints have the same sequence number, they will work at the same time. Since it is a zero on position, it will be done by user, and so yeah, we can say 1. Let's confirm. Now let's go to number 2, that, as we see here, is the axis of the elbow. Here again, let's just make easy things. In this case, I'd like to go from minus 150 to plus 150 degrees. I'd like again 1000, acceleration 1g 981, and jerk again 420,000. And again speed 550, 500, 500, 2500. And again the zero cycle will be done on current position, execute on sequence 1 and preset value is 0. No important settings to set. Now pay attention to joint number 3. Joint 3 is the Cartesian joint moving up. So first of all, let's go here and check. The lower and the upper end of strokes are not meant to be degrees, but are millimeters. So let's say that the lower end of stroke could be 0 and upper end of stroke could be, for example, let's say 700 millimeters. Then again, maximum speed of that kind of joint could be 1 meter by second. The acceleration can be 10 times, so let's say normally always 1g. And the jerk, let's make it a little smooth, 200,000. And again, here we would like to use 50 millimeters, and then, 50 millimeters is so few, 200 may be a better number. And here I multiply by 5, and so it's 10,000. 0 cycle will be again on position. Very well. Finally, J4 is the wrist. So here again we are getting back to degrees, and so let's go from minus 120, no, let's go more, minus 179 to plus 179. Maximum speed, okay, this may be 1000, and the acceleration and the jerk is made like this. So here I'm setting these values, and now the manual speed. This again could be 50, here 500, here 500, and here 2500. The 0 cycle will be again on current position, coherent with previous ones, and the execution sequence is always 1. Now let's go to Cartesian. Here in this tab we may write the values of the limits of x, y, and z. So this is relative to the Cartesian movement the axis group will perform while moving in Cartesian mode. So here we may set the speed, acceleration, and jerk of the Cartesian movement we would like to perform. So here maybe we'd like to set again 1000, maybe even more, why not? Let's say this may be 3000, and then here 30,000. And jerk, okay, it could be 420,000. Again, the manual speed, acceleration, and jerk could be some kind of values, like 500, 5,000, 5,000, and jerk again 25,000. Alright, now let's do the same also for y and z. Let's enable this, and let's put the same numbers. So this one, 500, 5,000, 5,000, and 25,000. While here we put 3,000, 30,000, and here this one. I think it was the same, yeah. Now Z did the same. Okay, oh sorry, that's the deceleration, so I copy, take out and paste, and here again. Alright. Now, finally the wrist rotation. So here again, even if it's something Cartesian, we have to take into account that that's not in millimeter, but that's in degrees. So again, let's talk about degrees. We may use 1000, 10,000 and jerk, okay. More ones, and here 100, 1000, 1000, and 5000. This could be so much. Let's say, no, that could be good. Confirm. Now let's go to the tool. Here we may set something due to the tool dimensions. In case we mount a fixed tool on our robot, we may write here the X, Y, and Z dimensions, or A, B, and C angles. Otherwise, if you want to set it at runtime, you may do it in your task. Here again the reference system. In case your robot is put over a column or down from the rooftop or on another point and you need to modify the reference system of your robot, you may enable this flag and modify, writing the position of X, Y, Z and the angles A, B and C. Finally, you may have some options that could be very useful in order to give some characteristics to the RPE behavior. For example, we can abort the path while we reach an end of a stroke. This is a safety settings that we may would like to choose. Another possibility is not to abort the path while we're going missing power. This means that even if we press the red button and we get in the emergency mode, we are not going to lose the move we are currently doing. But this means that at the next power on, we are requested to make it start again from the current point. Then, let's see, AG stop on angles. Enable path execution stop on sharp angles? No. Path execution limit depending on the acceleration? No. Some other interesting things. Here the use near angles, this could be useful. And here, let's see. A G handle fast stop, yeah, that's the enable of the emergency fast stop while power is falling. This is the automatic fast stop that we would like to use, so we are not going to request this while the system is going in fast stop due to an alarm. And now, here we may go to the last part, which is a definition of some labels, integers, or something else. And here we may confirm. Length 1 is not a valid real number. Oh, sorry. Yeah, here we still need to write the length of L1, L2 and L3. So, for example, let's say L1 is almost half meter and L2 is 44 centimeters. And finally, R3 could be just something tiny such as 25 millimeters. Okay, now let's confirm. And let's save. Good. Now, let's open here the Fieldbus editor. And here inside, we are going to put some motors. Let's open the servo drives. And let's take some drives, okay, some IMD, let's put number 1 here and check the slots, the profile, the module 1, the CAN OpenCOE, the module 2, and here the CSP module control, okay. Here is our data startup, that's the standard things we already saw and we already learned in the videos of RDE and R3 programming language. Here at the end we may check the I/O and OK. Status word, current position, control word and target position. That's good, I confirm and I just do copy and paste to make box 2. That's box 2. And then paste again to have box number 3. And paste finally to have box number 4. Now let's connect 1, 2, 3 and 4. Very well, let's do our network and let's fix here, for example, a 1 millisecond cycle time. Here there is nothing else we would like to do, so we may just confirm and save the file. I accept the restriction and I close it. Now let's go back here to EtherCAT and let's choose the 4-axis. Okay, this is 4-axis EtherCAT. Very well, and let's confirm. Now, I remember before in the configuration of the Fieldbus I cancelled this, so I have to enable. Now let's confirm and let's check that in the flash files we are going to have the EtherCAT CFGX, FB, IP address and RTE. No other file has to be generated. So as you can see, the configuration for the RPE is almost the same of R3 language. The difference is that now we have the set of axes called a robot and that we are not going to make the rule, but now we just begin to write a task. I do a right click here on programs, I make new R3 program. So This will be our task. Let's call it task 1 like always. And here let's choose FA as the flash folder we are going to save this task in. And this is robot task. And OK, automatically generation of the implementation source file for an R3 task. OK, and overwriting existing files. Confirm. Now, let's open this file. Alright, here is a task 1. As always, I like to play with my external editor in Notepad++. And here, let's take out this dummy part. Let's copy this comment in order to put it here. Too big. And I don't like this. Okay, let's copy this. Let's put it here. And here again. Alright. So, that's the init task. And here there is a task handle that we are going to rename and use very soon. And here let's put more blank lines in order to have a better view on what we are writing. Now, okay, let's begin the task. So, just set initialization code here, alright. Set version. Here, let's say 1.0.0 and just give a number as RPE lesson. Now, here, let's write power allowed equal true. And again, let's start the power set, PS power enable, PS1, and I say true. And then PS channel enable, PS1 mask def axis. Okay. And finally, as we said, the power allowed. And since this time we are not doing rules, we just need to say that robot.request mode is AG miss power. Oh, maybe I wrote it wrong. Sorry, I do not remember how to correctly call it, but we go and see the manual. And here we see the operative modes missing power. Alright. And here it's the operating mode. AG miss power. Oh, it was just one S. Miss power. Alright. Note here that I write the requested mode, not the operating mode. As we can see here in the manual, the request mode is the one we write when we want to change the operating mode, while the operating mode here, the open mode variable, is read-only, RO. So this means we are not allowed to touch it, but only the RPE itself is going to use it and check whether it is allowed to do a change from one possibility to one state to the other. This is something very good that will make the RPE system very safe, because even if you write something wrong in your code, you are not going to make any problem in the real robot. It will just avoid you and forbid you from going to a forbidden state. Now, let's go to the handle task, that in my opinion may be, as always, the mode change. The mode change function we are putting here is something working on a select. And so, let's do a select on robot.operating mode. And here we may copy and paste the modes of RPE. In order to make it easy, I just copy them from here and I just paste. Now, let's say that here this collision, I don't care. The passive mode, we also don't care today. the disabled we also do not care, and we just want to play with the other. Alright, case and all of this. Now, that's missing power. Here we go with manual. Here execution, which will be the automatic mode. 0 weight, as I said before, is the mode we want to use in order to see to do some preliminary operation before the 0 execution, which is this mode. And in case we want to move manually, we have the manual no 0 here finally. Very well. Now, per each mode, we are just going to do something. And here again, if we want, we may do something in order to ask to change from one mode to the other. And remember, every time we want to change, we just need to change using the request mode. Now, let's go forward and let's do some kind of operation. For example, in case we are in manual mode, let's check if we have the manual request. So I want to register our manual request. In that case, we are already manual. So in case we don't have that kind of request, we are going to ask if robot request mode equal to execution. And so in this case, we want to switch from manual to exec. In the same way, in the execution mode, when we press the request manual, we would like to go to the manual mode. Now again, in the 0 weight, while we move between the 0 weight and the manual no 0, we are going to do the same stuff. So let's just copy here from 0 weight and manual no 0. In case we have manual no 0 and we don't have the manual request, we go to 0 weight. And in case we have the 0 weight and we have the manual no 0, we will have the request to go to manual no 0. Okay. So in the 0 execution, let's say that we do nothing. That's because it is done on position. So there is no operation we have to do. And here, mainly, now we have, it's pointless for us to do this, but let's say that if I have, for example, an input or a better register to have a 0 request, we would like our mode to go to the homing, to the 0 execution. And in that case, we are just asking the system to make the 0 position. But as I said before, this part I will just comment because I do not want to do this now. Okay, so this is 0 request, 0 cycle. Okay, 0 cycle request. Now, in the axis 0 execution, we do nothing, and at the end, it will automatically move away. So, if done, it will change automatically to execution or manual, according to what we have chosen. And so that's the initial part. Now, let's go and see something more. So, in manual and in manual no 0, we would like to use a handler of the manual mode. So in this case, we will call a handler, let's say, yes, ANGD manual. And this function will be the same called here too. Now, let's go here and let's call it function. Let's put this nice comment in order to keep it more beautiful. Now let's have more empty lines here below. And here, for example, we would like to set the jog commands. Now, since we already defined the robot, and here we have the manual speed acceleration, deceleration and jerk, both for the Cartesian mode and for the joint mode. We just need to set the commands. Now, let's keep looking at the axis group structure, and I repeat again, starting from the RPE manual, we may just go here in RPE structures. And here the first is the axis group. Here in the axis group we may see all the values, all the properties of the axis group. And so, for example, here we have the manual jog, which is manual axis movements. These values multiplied by the speed or speed Cartesian to give the actual manual speed. Okay. So now let's just take this and let's make it equal to +1 or -1. So let's say that robot.manual jog. And now let's check. You see indexes ranging from 1 to 30. This is because we may have up to 30 axes in our axis group, and so we will have 31 axes, and here we can control each one. Now let's move it number 1, and this will be R jog positive 1 minus R jog -1 and nothing more. This is just something we would like to be +1 or -1. In this way we will give the command to the axis group, and the axis group will be able to move the robot. Then together with this we may have some other commands, so let's write a comment here, jog commands. And here, for example, we would like to make the joint and Cartesian movement. Now, in order to change between joint and Cartesian, we may see the manual flags. Here we have manual flags, it's a U32 and it's again like a bit mask. We would like to use each bit in order to have a specific behavior. For example, bit 0 is slow and fast. While we press this, we may have reduction up to 10% of the speed and accelerations. In this way, when we want to make very precise movements, even using jog movements, we will be allowed to do it because the speed will be 10%. Alright, so let's say that we want to copy this, and so we will say if something, let's say some value, the robot.manFlags will be equal to itself or I only want to add this bit. If we have a slow R slow fast, let's say, fast and slow because I press it to make it slow. I want to use this, else, otherwise I have to take it out. The best way to take it out is to make R end and R not. So I will make this flag the reverse of itself. Instead of just the flag, the bit 1, and it will become its complement to 1 said in binary. So this means all 1 and just 0 to the last bit. In this way, making the R end, so the end function bit by bit to the flags, all the other flags will remain while the last flag will be set to 0. Here we do like this. Then, for example, we may use the same behavior to make the joint cart, and now we would like, the manual slow. This is fast and slow. And here the joint cart. So here is Cartesian. If we want the Cartesian movement, I will copy this and so use Curtle, take it out. Other possibilities could be to use the tool Cartesian movement, which is related to the tool reference frame. We may use the single motor movement. We can use the manual step. That's something interesting, because this is the so commonly called grid movement. This is grid. So if we want the grid, we have to copy this, paste here, and now cancel this, paste, and put it here. So here is the step. And according to step, we need to set how much should be each movement in the step. Remember that the step movement means that at each pressure of the button to move in jog in one direction, positive, or the other, which is negative, the machine will move in that direction of a fixed distance. Now we need to know the grid step, and here it is, manual step. Step of the manual stop grid. Unit, joint, or cart based on the actual movement. Alright, so this one will just be a value we have to set. So let's, for example, set RR step length. The length of the step. This is a register. In the same way there are also these ones and all the others here. So as always, we need to define a file to include a file to be the library of our registers. Here let's make include, and let's call it litereg.history. As you can see, I'm not using this kind of character, the double epics. That's because it's not necessary. I could use it if I want to specify normally some kind of path. But since this file lies in the same folder as the task one, we can just call it like this. Now, let's save. Let's go back to the programs here. Right click and let's update dependencies. Inside dependencies, now we can see the litereg. The configurations depth is a system file which will be generated here by the configuration later. Now let's make the litereg. Let's begin, create a new one, open the editor. I will never know why it asks me twice, but okay. So registers. And now let's go and let's declare all the registers we want. Now let's go here, let's go down, we have manual request, alright. Lit manual request, this could be R1.0. Oh, sorry, then we should never forget that we already have other two registers, the power request, which is like always R10.0. And, of course, behind him we have the R feedback of the software. That's just a feedback I like to use, not to give the power, but to take it out. So, in case I just control that bit and I make it go to 0, I will just neglect the power or force a fast stop and take it out if the machine is already powered on. Now, let's go and take a look at the other registers we would like. Alright, here we have the task 1. Let's also move the document to the other view. Alright, so now we may have them playing together. Let's make this a little bigger so you can see it better. Now let's go down and let's copy all of them here. Let's make more lines. Okay. And here, this and this. Very well. Now let's define them all together. Let's make like this. Let's make R1 and let's make all the column. I press Alt-C to start from 1 and make all the progressive numbers. This way it's easy to make indexes. Jog commands. Now, after this, we have other stuff. So here, we can keep them together, since there is no missing register in the middle of them. And here we have R1.7, that's fast and slow. And here, finally, we have the Cartesian and the step. Alright, let's write here. Since luckily they share the same length, I can do like this, and yeah, that's 9. And so, okay, the first is Cartesian and joint, and the second is step movement. Enable. Good. Now, another thing we have to check is whether the robot is stopped. Since RPE is automatically making the change between the modes thanks to the request mode that is used and processed by the RPE itself in order to modify the operating mode only if allowed, this does not allow us to write bad code. So we may write something clever, call a common prologue. This function will be the initial function. We copy, we put it here. Let's put something else that we would really like. Function. Now, for example, apart from the very beautiful comment here and the very nice end of function that's always necessary at the end of the function, we go here in the main and I put a restart point. This is an important command. As you see, that's printed in red. That's a keyword of the R's real language. The restart point is something we will use here. Let's go to see. While we make a modification in the task, and we want the task to be loaded at runtime without rebooting all the system, we can do right-click, compile the task, something that I cannot do right now because we are still writing things and I would get so many errors. Then I can go here and say load in flash and restart synchronized. This means that the new task will be taken into account, and while the previous task will reach this point, the new one will take its place. Please remember, if you want to do the task update, load in flash, and make it reloaded at the same time, synchronously, and so to keep using this possibility without rebooting the Robox controller, you must pay attention that you do not have any very important variable stored here locally. If, for example, I have a variable which is an important value, like this one, when I will reboot, I should keep into account that this value will be set again to 0. I will lose its value. So please, if you have something important, either you put it here, like this variable, but in this case you will never be allowed to do the synchronized restart of the task. Otherwise, you store all the important stuff, not locally on these kind of variables, but you write it here in some register. In this way, they will never be reset, unless you make your system to start again and you reboot all the controller. And if you want it to be kept in memory even in that case, you just have to make it not volatile. Now, after this little hint, let's go again to our task and let's check what we are doing. Here in the common prologue, we want to check. We said we wanted to see if the axes are stopped. And only in that case, we would like to change the mode. It's pointless to ask to go manually if we are not stopped. So, for example, I don't want to put the break case here. Let's say that I will ask manual only here and when the axes are stopped. In the same way, I'd like to do it to check this condition from manual going back, let's say from the manual going back to auto, While instead in 0 weight and manual no zero, I'm not caring too much because I know there will be no other thing and I will have not too many problems in changing from one to the other. In execution, it's very important because here later we are going to write our automatic cycle. So we should be allowed to make this kind of request. We should never do it without any control because maybe we may interrupt and do something very bad to our system. Since we know that RPE is taking care about what we ask to the request mode, this does not allow us to write bad things, so please always write correct code and pay attention not to make strange changes, even if you think they are safe. In order to see here that axes are stopped, we look at the status. One of the most important variables inside the axis group variable and the axis group structure is the status of the axis group itself. Now let's go up and see it. Here we have the status. It's a read-only unsigned integer 32 bits, which is again a bit mask. So every bit has a meaning, and what we would like is to see axis in position. This is the end of the execution of all the motion requested to the robot. So we want this and we want this flag. Alright, in this case we are sure that the robot is not moving. If we want even more safety, we may do a rise filter. This way we will be sure that the robot will be already stopped since some time. For example, I can make a filter in TFB even just for little time. Anyway, I'm just going from manual to automatic. It's not a 0.1 second that will make my system too slow. But if you want, you may just not use that command and just use it like this. Alright? But for this sample, let's keep it. So, rise filter means I want this condition to be true for the variable which is time, but I can also use a position, an IP, or something else. In this case, I want this variable for this length to always see this one true. So, in this way, I can neglect the little spikes in case the robot just stops for one instant between one move and the other. Now let's copy this, and since that's a system flag, I like to define it separated. So here this will be the R2.0, and so I would like to separate from the rest. Now let's go forward. Here we have manual request, axis stopped again. Here we have all the jog. Very well, I see many values, many things have already been done. Now, for example, let's try to compile and begin to play our system. Let's generate all. I still have some errors. Oh yes, I did the data cut. I put it here, but I never connected my axis to the real ones. So associate this to number 1. And now, for example, let's just choose box 1, the status word of box 1. And here again, the control word of the number 1. And while linking, let's put the position actual value and the row IP, which is the target position. Apart from this, you see I never play any other value. For example, here in parameters, you know there are some very important ones. I don't want to play them. That's because some parameters like maximum speed, maximum acceleration, minimum and maximum strokes are already set inside the axis group. And writing the same variables in two different places could be dangerous because maybe if I need to modify, I will make a mistake. I may forget of modifying both, and if I forget, it will be a problem because I will not see the system working as expected. The only thing I can choose here is the servo threshold, and I say, okay, if the axis goes away of more than 5 degrees, please stop everything. But we already know that since we are just making an emulated system, we are not going to care too much about this, but on a real machine we need. The last thing that must absolutely be set is the k-bit to unit, which is the ratio between the unit of a single turn and the bit of the transducer. In this case, I want today to play it inside the init of the task 1. In this way, it is different from what we have seen in other videos, and I can show to you more ways to write the same things. About filters and alarms and definitions, everything is correct. Now, let me do the same here. Let's just enable this, set to 5, go here, set to, ethercat, box 2, status word, control word. Alright, here we have the position, actual value, and here we have the target position. Very well. Now this is axis number 3, so in the Fieldbus I connect it here, number 3. Please remember always to check the color of this kind of icon. This is yellow and also number 2. That's because they have already been linked here by axis 1 and number 2. So now we have to choose the white one, which is not yet used. Here we go to see the status word and here the control word of the axis. Now let's go to the link part, and here we have the position actual value, and here below we have the reference target position. Finally axis 4, and then we are ready to play. That's number 4. That's of course the last white remaining and not yellow. Status, control word. Now let's go to link, and here we have position actual value and target position. Very well. Now let's save the workspace, that it's something very important to do so often. And here now we have generated everything and we are happy, we have a good configuration. Now let's go and see the programs. We have the task and let's compile. Oh, we have an error. An index is expected in line 158. Oh yeah, the manual step is 1 per each axis again, and so we need to do 1, 2 and 3. 1, 2 and 3. Actually, we also have axis number 4. Oh, sorry. Yeah, in this case it will be expressed in degrees, but we still need to check this. That's another hint. Here again, while we need to add some axes, to add some registers, since we always call things by name and not by the index, it is so convenient because I can just copy +3 and -3, put them here, call them number 4, and now I can just take the list and modify it starting from 0 and going forward. Alright, so all the indexes are good, and even if we do the panel on the RDE, or even if we link some of these variables on the oscilloscope, we will never have the problem of thinking about losing it or losing its address, because this is something compiled and already done by the system. Now let's try again to compile. I still have other error. Yeah, I never set that register. So this is NVRR, because this is a real value and it is something that we do not want to lose at every boot of the system. So this is millimeters. Actually the last will be, millimeters is only this, and this are degrees. Okay, let's make it different. Degrees, degrees, millimeters, and degrees again. So in this way we may have the two ones. This is the degrees step angle, and here we will have the other in NVRR number 2. That's 2, that's millimeter, and that's again in millimeter. Very well. Now, if everything is good, we should compile it again, and hope this time is good. Yeah, that's good. We have generated the task1.elf compiled file, which is 71 kilobytes, and here now we have all the files we need to make our system start. Now, to load the file, let's connect to the RP2 that is already switched on and linked to my PC connected with the Ethernet cable. Now, since the RP2 already has a previous project inside using the same IP address, I'm able to connect it. First of all, let's check what's inside. sysinfo, system information. Here I can see very useful informations. For example, here we can see something about BIOS, OSF, and here we have the RTE version, the Robox operating system. Then here below it, I have Markov based workspace version 147. That's the workspace I put inside before. And now, as you can see in the task 1, if I click here on the left in the function list and I go to the init task, you see the set version 100 of RPE lesson. This means that this is the string and they are the numbers that are going to happen here in our project when we are going to ask the sysinfo. That's a way to recognize what kind of project is now running on the RP2. Apart from this, we see there is nothing more. So, let's, for example, come here and let's check what's inside the directory f8. Here we only have the RT, the operating system, that in fact is the one listed here, 34.28.4, but unluckily we do not have the RPE, so we need to load it. Let's do fload ***, which means I'm going to choose the file and I want it to go inside the f8. Now, getting up from the RD, I can go to the Robox common material. And here I can go to the RPE and I can choose, for example, this good version. This is okay, that's a beta, but it's still good. And now I'm loading it inside the f8. Since this is just a test project, the RHW is just saying that that's an RP2 and nothing more. So I'm not caring too much about what's inside and I don't want to update it. This is why now that we are going to do a rebuild of the project, I will choose only FA. Remember that doing the rebuild means that I will erase everything inside the folder before writing inside the requested files listed here in the Flash window. But remember, never do this in F8, otherwise you would cancel the RTE and the RPE or any other kind of important file you have inside, and you will be not able to start it anymore. You will need to connect, to unplug the memory card from the Robox controller, connect it to your PC and load it manually. So please always remember never to do the rebuild and check in the F8. In the FA we clear everything, set the loading mode to make loading faster and stopping the execution, and finally we are going to reboot the device at the end. Since this is the first and also the last rebuild we are going to do, I wanted to synchronize the date and time with the ones on my PC that are correct. Okay, let's confirm. I already made, by purpose, a little mistake, because I want to show you how to correctly debug. Now, after this rebuild, the system will reboot. And now we will see. Here the RP2 is now making blinking and flashing some LEDs, starting again, telling me something about the OSF, the version of the system. That's something we can see on the screen of the RP2 or RP0 controller. In case you have an RP1 controller, you will have a double 7-segment screen, and so you will be able to see numbers from 1 to 64. Those numbers are representing the kind of alarm that is the most important now. Let's say the first alarm of the list. Now my RP2 is telling me some information. I can ask ALS on the shell to see the alarms, different user registration and alarm history loss. As we know, this means that the system recognized that I put inside a new project. So the project on the SD card is different from what it is expected by the RP2, and it's what expected because it was already copied inside by the previous project. Now I press twice the button below the screen, which is the Advanced button. The Advanced button will reset the alarms and then will allow the system to try again to start. Now the system is moving so slow. Let's ask to the report why this is happening, and let's make the debug of the requested mistake we are doing now. Now we have the report, and inside the report we can read many things. Like always, we may have very important informations about the memory, about something of the power enables. We may see something about net control and the connection requested by the EtherCAT Fieldbus. We can see the license we have in our memory. Then the RTE start what's inside. We may see more information, language, alarm history. And now here we load the RPE. And later we got to see some problems. Okay, it's telling us that things have been reset. And now, beginning again, we come here and we see transducers ready wait, expected 0xF, and we have 60-second timeout. That's something that's requested here. We say that when we boot, we want 60 seconds, that we can also reduce to 10 to make it faster, and we want it's the due time to expect all the transducers to be correctly seen and connected and reachable by our controller. If at the end of this timeout transducers are not ready, we will receive some alarms. The same that's happening now. Let's play ALS, and we see alarm 18. If I want to know more, I can ask AL info 18. And here, automatically we have the book of the RTE showing us what alarm 18 means, and that's the problem of the Fieldbus network. And it's telling us also the number of the workstation, 1, 2, 3 and 4, of course. That's because we have 4 axes, and all the 4 axes have problems with transducers. That's obvious. We are now making a simulation, so we have no motor. On a real machine, you may check this and understand you have a problem on your EtherCAT number 1, since you may have more than one. And it's also telling you which axes have a problem. But now, since we are emulating, we may do 2 things. One is to do shift and space. As you can see here, while the axe becomes with this white icon, it means that's emulated. Or if I right click and I ask for modify, I can go here and press check or take out the emulated flag. But if we want our system to be already compatible with the real machine we are going to put our program on, we need something to be used only offline, only sometimes while we are playing on the desk. And the same system must also work on the machine. To do this, the best way is not to make the axes emulated here in the RD, but instead we keep them as real axes. We go on Flash, and here in FA we want a new file, an override file. So let's go here, and here, next to the lit reg, let's make an override file. This override file will be executed at the boot. The name is very important. It must be saved as override.cfg. So let's save like this. And now here below I can write mask emulation axis, and that's 0xf. Again, this is a bit mask. So 0xf means binary 1111. So 4 bits to 1. That means all the 4 axes of our system are emulated. Now let's go to Flash. FA, right click and add that file. Let's choose the override CFG and put it here. Now I right click and I load in Flash. Not only, but since this file must not be present on a real machine, otherwise will make real axes to be cancelled, neglected, and will make problems to force the emulation, I press space, or if you prefer, you can just enable or disable doing a right click on the file and checking this. Since now is disabled, you can see its name is gray and there is the red cross. So the system will not automatically load it in Flash. Only if you want, you can load it. So we can check fdir/fa to see we have now the override. If for some reason you use the same RP2 and on your real machine after the test and you just want to kill it, do fdel. In this way, it will be deleted. Check again with fdel to be sure that the file exists no more. But now, since we need it, let's do again a right click and load in Flash. Now, since I also modified in the general part the timer, I can do a right click, generate the RTE configuration, and now press make. In this way the system will just update the requested files. Stop everything, and now for this time let's also keep these flags. Okay, now after this new boot we expect the system to behave a little better. Now let's do a clear. This way we clean what's printed in the shell. Now let's wait a few seconds in order to let the RP2 to boot again, and now we should ask to it what we will see in the M report, and then we can also check the kinds of alarm we have. Now the system is already enabled and the mode LED is blinking. I can ask ALS and just see the emulation active 0xf. I have no other alarm. Let's check the report. And we see here transducers ready wait, expected axis 0xf, and we have 10 seconds, starting from 32 seconds after power on. But in the same time, you see always in 32 seconds and few microseconds more, the transducers are ready, because we already accept the override CFG and what's written inside it. Now we begin and we have user software version 100 RPE lesson, and as I said before, that's the string and the version number we have set here. If I finally ask sysinfo, we can see here RPE lesson version 100. Excellent. Now here we also see more lines from before. That's because we also have the RPE plugin version. So we know we have the RPE and we are going to be able to play our axis group. Let's begin making some panels to better debug our system. Now right click here and let's make a new panel. Normally we would like to make something like the power set panel, but today I don't care. I just want the graphic panel, a generic panel that we will rename control, CTRL, and that panel I will take out from this view. And here let's open the editor, and now let's put, for example, a button to check. That's not important, but we would like feedback and power request. That's feedback, okay. Copy and paste, and now we need the R power rack. Very well, here this. Now let's put here above something more. Here we put top center, no, top center this. The variable will be robot.openMode. And here again in the text we just write openMode. Good. And these two will go down. Now we never put a button to reset the alarm, so that's easy part. Let's come here and say lit R alarm reset, and that's R1.12. Remember that the registers are integer at 32 bits, so we are allowed to go from 0 to 31 per each register we want to use with bits. Now the alarm reset here in the task. At the end of this point, we should put another function, call handler alarms. We copy this and we go down, we go at the end of the universe here below. Function and alarms and the function. Now let's say if rise R alarm reset, we want to do alarm reset command and then a PS channel reset fault, that is PS1. I do not remember, let's just press Ctrl F1 and see the manual. Okay, I should do a mask, the mask of the resetted commands. Alright, so let's just say, please access in the group. Let's say everything, okay. This is mask def ax. Perfect. The tooltip was already telling me to do this. Old equal to 0 and if. And as always, here below, we can put right here other alarms. Very well. Now we can go here and make a button to make the alarm reset. Let's copy. And then let's also put some values. Okay, now another thing that's very important is that we do not have the steps. So I put 10 degrees and 5 millimeters. So we have these values. Since we didn't do the Loster egg to load some files here, we just play like this. They are just 2 NVRR. Alright, now manual request, okay, this one instead should be monostable. That one again may be monostable. And while instead here, be stable manual request. Okay. And monostable instead, we need jog plus and jog minus. Jog 1 plus, and that's monostable. And let's copy this. Very well. Now from this I can do the second one here, so that's neg1, that's minus. And now just copy and paste. Perfect. And now it's just some index stuff. Here is number 3. number 3, and number 4. No, sorry, 4. Very well, number 2 negative, number 2 negative, number 3 and number 3. Now number 4 and number 4. Fantastic. Okay, let's put a form here behind. We make it big. Very nice. Then we make another. We make it here. Nice. Now let's take, now you see I would like to click on the text, but I cannot. That's because the system is clicking on the piece, on the shape. So I go here on the shape and I can modify the priority. Now the priority is 0. I can say -1, so it will go behind. Now I can click and touch things because they have a priority 0. If you make a higher priority, you will make them go to front. Here again, we say priority -1, so they go all behind, and now here we can touch the buttons. Now, let's save. Now, let's come here and change the connection. We should not go in directly to the TCP, but we should go to the project, otherwise we would lose the name of the variables. Here the space is infinite, we can just reduce. So now you can see the dotted space maybe is so short, but at least we can go down with this. Alright, then alarm reset, alarm reset. Okay, I need to see if everything is correct. Alarm reset, okay, it's here. Now let's make. And after the make, we will be able to connect to see the updated program. All right. Now we can see here, okay, too late. But here below, we can see some information about what file was loading. And here below, we also see that task 1 has been made and loaded, and of course we have reboot the device. Together with this, let me check here. Okay, here we could put the codes like always. So 1 can be missing power, and then we care about 2, which is execution, and number 3, which is manual. I know these numbers because I saw them so many times, but if you want to see them, you can check here. Okay, and in fact I wrote them wrong because I say that 2 is execution while instead it's manual. Modify, that's 3, and that's 2. All right. Now let's see what happens. Play. Now it's missing power. All right. Let's see ALS. And we have just the axis emulation active alarm. All right. I press alarm reset. I press the feedback. I ask for power, and that's number 4. That's 08. All right. Now, since we are in 08, we can go here in the task 1, in the mode change. And actually, here we should enable this part. Okay. So we can do a complete simulation. This 0 request will be necessary here. And that's R1.13. Okay, 0 cycle request. Very good. Now let's take out the power. Let's make again. And together with this, we can just modify this part, copy and paste, put here the 0 request. No, I didn't. Control C. Sometimes the Control C is keeping something in mind which is not so nice. And we can put some alarms that could be important and interesting to be seen. ALS1. We can make it wider and then copy and paste, copy and paste. Oh, copy and paste. Okay, the first has a default position which was not so nice. Normally when you create a new element, it is not exactly centered according to the correct position, so we should always check, and maybe it's clever to press an arrow, like arrow up, arrow down, just to force it to go to a standard position. Now let's play and we say, okay, alarm, reset, now feedback and power, and now 0 request. And we have gone to one second. If you have seen wisely, here it was manual and now it's execution. That's because here we do not have the manual request. So if I go to see here the power set, we say that the first mode was manual without a 0 cycle. So after we make the 0 cycle, that's what just happened, the system wanted to go to manual with the 0 cycle, but finally, because we do not have the manual request, thanks to the software we wrote here, so we just went to execution. Now, in execution, we are now just having the manual request only, and later we are going to write some automatic cycle. But now we can just play with manual. The first thing we can check, we can see, is that we never had to deal so much with the power set. Let's say, apart from here, this enable and channel enable, here we don't need to check the power set status if the power is going down like we do in the RC language. Here all of this part is already handled by the RPE itself. So this is a very great help we have. So if you have the opportunity to have an axis group and you would like to use RPE in your program, it's a clever choice, because many things are automatically and you don't need to care about many basic things. Now let's make a right click and let's try to see our robot. So I make a 3D panel. All right, we put it away. Now we go here and we start playing with this. First of all, let's make black background. Let's take out only the grid that I do not like. No, let's keep everything in this case. And now let's add robot. Here we have the SCARA, that is exactly what we need. Here we can use anthropomorphous in case you have an anthropomorphous. Here we have another kind of anthropomorphous, you see. And here finally we have delta robot. Now let's just move it just to show. I can put it 1000 so you can see. And then here you can feed the position normally of the joints. Here they should be the IP of the various axes, but now we are not using this, so cancel, delete. Here again we can delete, and also this, that's pointless. Now I go here, I click insert cylinder, and now we have this small cylinder, so we can make it higher. Let's say here we can put 1 meter. 1 meter is giant robot. Now you see that the height is going symmetrically up and down with respect to the 0. We want it just positive, so the Z position must be increased by 500. And then I think the radius is so much we can have a thin robot. And now according to this, alright, here we have these positions, and here now we have IP1, no, better. Here, since we have the QJ, the best way is to use directly the robot.qj1, Ctrl C and Ctrl V, QJ2, QJ4, if I remember, no, QJ3, correct? Yeah, anyway, now they are coherent, and QJ4. Now let's take a look at the robot. Oh yes, the sides. I was not, now here we have lens 1 and lens 2. Now we go to configuration and we try to check again the model. Okay, so we have 500 and 440. Okay, tiny robot I did. No problem. Okay, now let's take it out and let's play. Oh, sorry, yeah, there is no connection. And here, since it's a graphic panel and we want to see it beautiful, we can make 50 Hz, which is enough for the human eye to see it with a nice movement. Let's make it bigger. Oh yeah, and now I can press manual and let's just go up. Very well. Now I can play J1, J1 minus, J2, J2 minus. One important thing we would like to have is a trace of what the robot is doing. It's very interesting to see the path while the robot is moving mainly in automatic and it's so fast. We still want to see what kind of position have been touched by the robot. So we have this, the point strip. I use it, and here in the point strip we can say how many points, let's say so many, 500, and let's say the distance between one point and the other, and okay, 2 millimeters is a good distance. According to the position, I can just ask robot.qc, so the Cartesian quote, maybe the tool point is better, tool number 1, Ctrl C. Of course, the tool is a Cartesian reference, so 1, 2, and 3 are respect with X, Y, and Z. And now let's touch here. Now again, let's go down. Oh, sorry. Yeah, you can see now we have this red line following us. It's showing a trace of the previous movements of the robot. So it's very nice also to debug. I put 500 points, which is so much. Now, if you see J4 is just moving the tool reference, which are these red and green arrows shown here. So I move it again. You can see now the red and the green have been rotated. That's just because it's the wrist axis. Okay, now let's do something more. As you have seen, it has been so easy to program that part, because in the manual mode I just ask manual, and here we just have some flags. Now, for example, we can play. Let's take a look at these values. Let's go and say dv, this value, and so we have the values we expected to see. Now we are not having any kind of view of the robot parameters, so of course we come here, we make it bigger, we ask for more vertical space, and here now let's put some values. For example, in this point we make it bigger to have a better editing. Top center, this is QJ1, and the variable is robot.qj1 as before. So we can see the joints of the robot. Now, like always, we move it a little forward and backward. It's a real value, so as we know, if we put precision -1, the value will have too many digits after the comma, so please just put, I think 2 digits are enough to have a good precision. Okay, that's QJ1, copy and paste. Let's have QJ2. Let's make all the ones. I know that these kind of operations may look boring and just some A candies, but I can ensure you that that's something very useful in order to better understand what the system is doing. As long as the system is behaving as we expect, this is just some graphic toy to make customers happy. But when system is not making what we expect, so this will provide you important informations. Also to see in fact the Cartesian coordinate. It's also good to being able to set the points. Now it's something that we are going to do because of the automatic cycle. And in it we will, for example, make a pick and place, and so we will need some points. So we need to give values to some real existing points and not going to infinite. All right. Now, for example, we can see the joint quotes which are in degrees, apart from number 3, that as we know is in millimeters. So you see here I can go down, for example, I keep going down, 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 down until 0. As you see, the system is not allowing me to go less than the minimum stroke. If I ask in the shell dv min stroke 3, or even better, since it is a robot, we should not directly look at axis, but we should look at the robot. So dv robot dot minimum stroke j 1,4 to see all the ones, and you see that joint 3 is 0. And so if I keep pressing negative jog, it will not allow me to do it. One other interesting thing that we still didn't make until now, but always very important, is the oscilloscope. So let's do one here. Let's bring it away. And okay, and now here in the oscilloscope, we can go to settings, put a high frequency to have not to lose samples, big storage. And now the connection is already done. So for example, the first could be robot.op mode, and this could have a scale of 5. Then number 2, and now as always we do robot dot let's put the velocity. So it should be, now we can check the axis directly in this case, IV1, and IV1 can be 100, maybe more, let's say 200 could be a good value. Now IV2, and again 200. Okay. IV3, and that's again 200. And finally IV4. IV4 is 200. Interesting. Now right click, I want to see variable names, and now I would like the operating mode to go up. And let's also put here a very important variable, which is the Vtan. Vtan is the tangential speed of the robot, robot.Vtan. This is the speed of the tool point, so it's already taking into account all the motion, so it's the speed of the point here of the tool expressed in millimeters by second. So this is the most important value, let's say, because from here we know how fast is moving all the robot. Now if I put it away, we can try to play again and move J3 up, J3 down. You can see that the motion is jerked. You can see that the speed is very smooth during the acceleration ramps. J1 minus J1, J minus J2 plus J2, and J3 minus J3, and J4 minus J4. As you can see, while I move J4, so now let's see the oscilloscope. Let's make it more concentrated. Here we have all the V of axis 1, axis 2, axis 3, and axis 4. But while we check them together with the VTAN, maybe the VTAN also needs a higher, yeah, this will be higher. Let's put 300, for example. Here we see that while we move J4, we have no motion in VTAN. This is because we are only rotating the wrist, so the position in the space of the tool is not changing. It is only changing the orientation. So if you want to see it together with VTAN, you can also have V-ori like this. So this is the speed of the orientation path. Normally we check VTAN, which is the limiting one during all the motion. Normally the orientations are just following, and so we don't care too much. Now okay, we can see that we are doing all of this kind of motion. Now let's see something more interesting. Let's, for example, do a mistake. Let's make this be stable. So now, while I will press it, it will remain pressed, and then we try to make a fast stop. So I press it and close it like this. Now let's check. Here I go to see, and here we can take a look that until this point we were making a smooth ramp due to the manual. We were going at constant speed, and while we lose the feedback, the system is automatically doing the fast stop ramp. So this is one of the features of RPE, and it's very interesting because we don't need to write again all the rules of the fast stop and writing the speed ramp and thinking about the acceleration and so on. Everything is already handled by the system itself because it's something we already requested in the RPE settings. And so again, that's something very useful because this is some powerful stuff already handled by the RPE. Now, okay, the last thing, the other things we can check now are some of the other Cartesian things. So now let's go again to manual. Here we have the fast slow, so that's quite easy. Now if I press it, and you see we can go like this. If I put it equal to 1, okay, and then I can move, I have the slow movement, and so you can see that now the J1 is moving in a precise way, and this is a way to make it slower. Now if I put it to 0, we will get again the normal movement. Remember that the robot also works with the feed rate, robot.fr. The feed rate goes from 0 to 1, and it is the coefficient of speed and acceleration used by all the movements. If, for example, I say that feed rate is 0.333, is 1/3, I can move the J1 at a lower speed, and now we will see that the value is this number. And this number should be, if you see, for example, the heavy one is 16 and 2/3, so this means that should be 50 here, and in fact it's 50, you see. So the standard speed has been reduced at 1/3. This is a value you can play when you want, you can set in order to make the robot faster or slower, maybe in some difficult points while you are moving in your cycle, in your automatic cycle, you can reduce it when you are close to some crucial points. Now let's go to see the Cartesian movement. Now the Cartesian movement is just, oh sorry, I went of course to the wrong direction. Now let's go negative. Oh, we are moving very, very fast here. Let's give again some power. And now let's, for example, take out this Cartesian. I want to move to a safer position. No. All right. And now again, let's play cart. Let's say J3. Oh, it's going so fast. Let's also see here. Yeah, that's too fast. Number 1. If I now play, I can stop and play to cancel the point strip. Now we can see, I move it slowly. I move it like this. So if we see it, if you see the point strip is now moving Cartesian. So J1 means plus and minus X. So you see we are moving in the same direction of the X-axis. And of course J2 becomes Y. So we move along the Y-axis. You see right now. And J3 of course remains Z. Since this model is already SCARA, so the J3 is already Z, there is no difference. But you can see the difference for J1 and J2. And also J4, you see, is always behaving in the same way because it's the wrist, so it's the only axis moving the orientation. But more different and complex robot structures may have different kinematics models, and so while you press the Cartesian, while you play Cartesian, you may see the joints behaving in this different way. So J1 is X, 2 and 3 are Y and Z, and eventually 4, 5 and 6 will be the 3 rotations, if available, around the Z, Y and X axis, so the A, B and C rotation. Now let's put again the Cartesian to 0. Of course, normally we suggest to make buttons, okay? We can also do them here and put R step, and they are bistable, of course, because they are some settings we would like to play. And so let's take, for example, our cart here, and we can play. And here there was R fast slow. Here, copy and paste. And here let's make, I don't want capital, let's just call it fast and slow. And let's make the sides big enough. Okay, so here we can play the step, and now according to this I can move according to the step value. We saw before the step value is 10. So this means that now J1 is in minus 30. If I press, it will go to minus 20. And then minus 10, 0, plus 10, plus 20, and so on. So this 10 is the step. The same for J2. Now J2 is 71. Okay, I move negative. It's 70 because it's the closer multiple of 10. And then 60, 50, 40, and so on. The same for number 3 and of course for number 4. Very well. Keep in mind that the number 3 has a man step of 5, so it's now 665. If I move down, it will go to 660, then 55. Now I pressed too much, so it made 2 steps, 45, 40, then 35, okay, 30, and so on. So this is again an interesting configuration you can use during manual movements to play with your robot. Now you see the function we have written to handle all of this is so small, and of course if you play in the RDE with the predefined workspaces according to RPE, you will find always a similar structure to this. So while you need to make your robot programming, you don't need to start from zero actually. You may copy from already existing ones. But of course, keep in mind you need to know what to do this command, how do they behave, so you need to know them. And if you need, there are some other interesting flags you can use in your manual movements. Now, for the final part of this lesson, we would like to make an exec, so we would like to make the automatic cycle. And here we go to execution, and instead of handle manual, we call it handle automatic. Let's copy this, let's go again at the end of the universe. Here we press it. Here I'd like to go to put a end of function. Let's give more space, and of course this is a function declaration. Oh, I did something terrible. This is function. And yeah, of course, I always like to keep these comments. All right. Oh yeah, this is the alarm function. So the alarm function can go last. And here in automatic, let's start to play. So while we move with RPE, we said we can have two kinds of movement that are also the ones we are playing in manual. So we can move in joint movements. So when I ask a motion, I just go from one point to the other point. The system, the RPE, will calculate the necessary quotes in joint, and every motor will move independently from the others to reach its own target. This means that you will always reach that target, as long as it is possible to reach, of course, but you don't know the trajectory that the robot is doing. So it can make some kind of curve, some kind of strange movement, and so you can do the joint movement only if you have no constraints. Normally, you are afraid to touch a wall or some other machine, or there is always some kind of constraint in the space. So for this reason, normally people would like to move in Cartesian. And so people will ask, okay, I'd like to move from one point to the other point just according to a line. Now, sorry again, I broke everything. I reached the maximum point. Now, you see, I'm just playing with y-axis. Now I should play x. Alright? So if I have one point and another point in space, maybe you would like to move it in Cartesian way. Remember that Cartesian movement is not always possible, as we have just seen. Points could be outside of the task space, or even worse, in order to reach them, you can pass through some singularity of the system. That's according to your robot model, of course. Or remember, if you are in a point behind the robot, now let's go again to Cartesian. If, for example, you go here, which is behind, and from this point, I want to reach a point here where I have the mouse. If I move joint, the J1 will just make a wide circle and reach it. But if I ask Cartesian, I will ask to make a path, which is the row connecting the 2 points. And this row may pass through the center of the robot, which is of course an impossible point for the robot to reach. And this is something terrible we must never do, because the system wants to reach that point. And if we put correctly our max strokes, our limitations, it can avoid it and make an alarm. But if you didn't, this could be very harmful for your system. So please, as always, the best way to avoid the problems is not to write bad software. So keep in mind that ask a Cartesian movement only when you exactly know the begin point, the final point, and you know you are not going through any singularity or you are not doing any impossible motion for this. Now, apart from this motion, let's go and make this automatic cycle. In the automatic cycle, we would like to do two things, let's say. The first is a choice, and the choice will be between some kind of pick and place motion we are going to do thanks to joint and Cartesian movements, and then we would like also to play a path. So now let's do, if let's say that the motion here could be handled by a select, which will handle a state machine. So I will call our status auto. And normally we would like to go to case 0. And in case 0, we have to make a choice. And the choice will be if r pick and place. So we are just going to set the points we would like to reach. And now we are just going to the, for example, we change the state to number 1 and we are going to set it. Number 1, break and if. Of course, we should remember that there is always a break, and at the end of the universe there is the end select. Now, in case we want a pick and place, imagine, for example, we have some control to a cloth, some kind of tool, okay, to pick the product, and so we say lit r command close, and this is 14, and this is, let's say that's some automatic stuff, so I'd like to put it here, r2.1, and so that's open close command, okay, just to make easy things. Ctrl C. And in case we begin, let's just make it easy and let's make it false. This is claw open. Now, of course, in a real machine, we should check if the claw is closed, if there is already a product inside, and so on and so on. But this is just a sample, so we do this way. Now we go to case 1, and case 1 will be the request to go to the first point. So go to over pick, and then we should also need to set the points. We go up, we go to the init. No, even before, here we need some variables. So to define the points of the pick and place, let's say that first we would like a point J, so a joint point, which in my opinion is the home point. And then we need the point Cartesian, which will be the, let's just say P1, P2, P3 and P4. Let's make it easy. And we copy them, we go to the init, and we say P home dot qj1 0, and then 2, 3 and 4. So let's say that this is the home point we would like to reach. And then here we can say the P1, here we can just say that since they are Cartesian, we can write directly X, Y, and Z. And so we can say, we can check, for example, okay, this could be a good X point, for example. So 8, let's say between 8:30 and 2:10. 8:30 and 2:10. Of course, that's Y, that's Z, that's A. Then this is overpeak. So we want, for example, 600. And the point A and PA is 0, okay, 0 degrees. Now, for example, for the point 2, let's just copy, paste. We can just make it like this. We can, to be sure we are doing the same, we say that the point 2 x and y is equal to point 1. And why not also the last? While here we put, okay, 0. Let's say 10, just to keep some distance from 0. Then the point 3 can be on the other side. So we go here, we move manually, and we move J1, as we said before, okay, something like this. So 100 and minus 50. All right. P3.x is 100 and minus 50 x, y, z, a. Let's say we would like 90 degrees, just to play a little also with the orientation. And finally, we just copied P3 to make P4, and we say P4 will begin from P3, here and here, P3.A, and that's, for example, let's say 50. Imagine we will place the point a little higher on some kind of base. Okay, so pick and place points. And this is the home point. Very nice. So now, in the automatic cycle, we can say, we can make it better. The first thing is not the choice, but will be move to home. So, let's check, for example, first, if we are already in the same point, because we can ask if PA distance between the robot and P home is less than 5 millimeters, so we have no need to go anywhere, and we go to, for example, we say it status 2. So we make it a little different. We break and if. Otherwise, we can do PA, move, joint. And here, let's copy this to go here in the manual. Now we don't need the oscilloscope. Let's press the book. Let's search P, move, joint. Okay. And so, axis group, the point, and then we have speed, acceleration, deceleration, and jerk, according to some values we can set. These values are the desired speed percentage between 0 and 1. The same is valid also for acceleration, deceleration, and jerk. So, this means that the maximum value, number 1, will use the maximum speed we set in the configuration, okay? So, if I go back to the configuration, and I show to you again the robot, we go here. Here we have set maximum speed and acceleration of the robot. And here we have some maximum speed and acceleration of Cartesian. So these kind of values are the maximum ones equal to the 100% in case we choose 1, which is 100%. And so all we would like to have here is that kind of percentage. To make it better, we just use some local variables. And so let's make real speed 0, acceleration 0, and ger 0, for example. And here at begin we say we write standard move parameters. Of course, we would like to use some registers and any other kind of value we would like. But now in this kind of example, we just say speed 0 could be for example 0.8, acceleration 0 is 1.0, and jerk 0 is again some, okay, let's say 0.5, which means half of the S ramp, okay, because in the jerk we can see 0 means no jerk, and 1 is the total jerk. In that case, we just say, okay, 0.5 to have some kind of jerk in our ramp. And finally, there is another value we need, which is the RR. This is the distance to make the overlap of the move. Now, according to move overlapping, we can learn a lot in the manual. So instead of doing one move and going down with the speed like this, and then stopping and starting with the next move, we can have this kind of motion where the first move and the second one are overlapped. So the deceleration of the first is overlapped to the acceleration of the second, and the resulting speed is almost constant if the parameters are the same. And in that case, we can determine the distance from the point where we would like to have the speed. Of course, we must always take into account that sometimes we should avoid to make too much overlap while the movement is requesting the axe to go to the reverse speed. Otherwise, the acceleration can become so strong. But today we just make some easy movement, and so we will just keep a small overlapping distance. Alright, so in this case again we can go to the beginning and say real TRS. We call TRS like over the overlap. This is the overlapping used also inside the path. So TRS will be, for example, 5 millimeters. Very well. No, sorry, I cannot call it R, otherwise R means register, but TRS is already a keyword, so okay, just call it overlap RR. Copy and paste. Very well. So when we do the move joint, we move robot to the P home, and then we use the speed 0, acceleration 0, again the acceleration 0 for the deceleration value, jet 0, and then the overlapping radius. Here again we may have a result like we are used to know. So there is a result which is the motion outcome. If it is a number which is 1 or anyway bigger than 0, this means that the path, this kind of motion, has been launched correctly. If it is 0, means that the movement cannot be queued. Otherwise, in negative, we will have some other kind of error. So let's say that we always would like to check this. So the result is coming from here, and here we check if the result is less than 1, we should do alarm set, and we call it alarm move wrong. Then we say 0, which is the parameter of the axe, and here we say result. So this is the first number is always the axis number. So if you write here a number, this means that that alarm will be referred to the axis here. If it is 0, means no axis. If something bad happens, we have, for example, to go to -1. And if, and let's of course break. So the case -1 is error case, and here we do nothing and break. Okay, we already know in this case, if we have the alarm reset, for example, we can say if the status out is less than 0, status out equals 0. Okay, this way underscore if just because it's one only command after the if, so we don't need the end if, and we make more compact code. And so, okay, in case we have an error, we have to say this. Now, here we have only lit reg, we didn't enable a lit alarm and lit IO like always, so let's do something bad, and here in the lit reg we will also declare this alarm. And so we will say, okay, this alarm is an alarm 4000. This means that this is a warning. So not stopping axis, not making a fast stop. Anyway, we are not moving, so we are going to state -1. But we are not cutting the power, we are not making problems. In this way, we can just read what's wrong. Maybe we can change runtime the points, because as you know, we define them only in the init of the task. So we can play runtime, we can modify on the shell, we can modify maybe in case we have an HMI, we can play on them, play with them, and so on. So okay, now this space is useless, and let's just declare this alarm. And about the user alarm, okay, you know, normally in the configuration we can come here, go in general, alarm file. In the user alarm we may write some kind of alarm here, and okay, let's do it. Let's behave in a good way. I make a new file and I call it alarm text. And so, you know, here there is the standard alarm file. We can get it from the RPE manual. And here we say in the alarm handling, we should find, if I remember correctly, there should be the user alarm file. And so, alright, we can write it here. Good. Like the alarm 3000, 7000. I was looking for a 4000 alarm. We don't have, so I don't care too much. I just copy one of these and come here and say, okay, that's the alarm 4000. I choose an alarm mask, but maybe it was stated here below. Okay, yeah, 53. User signals have the alarm mask 53. Alright, so that's 53, bit 0. So here we write the text, and the text will be error in move, and we can say error %d in move %d. So -4 because the first parameter is the error, and remember minus is because it is a a signed int. If I write only 4, it will be unsigned int, while the second, in fact, will be just 4, so the second %d is only an unsigned integer, which is a counter we would like to use in our move. So this means that in our move I will say this is the result of the move number 1. Okay? Later we will use the same alarm more times, and we will just use this index we will just modify it so we can understand which of the many moves we are going to do has made an error. Now I need to save this. I will go to the RPE lesson. Yeah, that's not a txt, yeah, it can remain a txt file, and this is alarm user, let's say user alarm US. Okay, so now I come here, and this is the RT, we don't care, and here in the user alarms we go to see the user. Okay, so we include this. Perfect. Very well, and that's here. Now, alright, we made this, maybe we will need it later too. So if we have some result, we go to -1. Otherwise, the status will go to +1. So if we will go, oh, here again, I was writing 2 already. Actually, yeah, this could be 1. This could be 1. And break. And now, case 1. And in case 1, we will make the choice. Oh, yeah. First, in case 1, we must pay attention that the robot must already have finished the move. So, we will want the axe stopped in case 1. And so we say if not stopped, break. So wait to finish. Wait to finish the move. That's because, as you can see, here we only give the command to do the move joint. The RPE will handle its own one. As we said before, the RPE is actually using only the task 1, but actually it is doing its own task and its own rule, so they are 2. Inside its own rule, which is a system stuff we are never able to see, it will perform all the motion. Here in the task, we just ask the move to happen, we see the result according to possible or not possible, and then we are just waiting the move to be done and to finish. The system will make automatically all the kinematics and the limitations, all the calculations, accelerations, decelerations, and we will just need to see. While we are stopped, it means we are arrived. Very good. If not stopped, break and wait to arrive. And now we say, if I have a pick and place, I will go, for example, to the phase 10. And in case 10, we are going to overpick. So overpick, again, is a move we should say we don't know in which point we are at begin, and no, but we know we made the home point, sorry. That's why it exists. So go to overpick, it will be not a move joint, but will be a Cartesian movement. And the point is P1. Remember that we can use move joint and move cart in both cases using point joint and point Cartesian, but we are also allowed to do some mixed solution. It is always allowed to move joint to a Cartesian point, but it's not said we are always allowed to use a move cart to a joint point. So please, it's better to keep coherent moves, so cart and cart point, joint move and joint point. But remember that going to a Cartesian point is also allowed to be done in joint. This is because maybe, as we said before, we don't care too much about the trajectory, we just want to reach it. And maybe we know the robot is in a place, in a point, where there is no constraint. And so it will be free to do any kind of geometry and trajectory it wants. Now here we say, okay, move cart to P1. And again, we say we almost copy this. And we say if the result is negative, so I have the result in the motion, and we will call this motion 10. So to remember that this is the first motion of the pick and place. And otherwise we will go to 11. And now, or even better, we can do them together, okay? Because we can ask a queue of moves. We are allowed to do this, but we must take into account, we must keep in mind that, of course, we must always check if there is something wrong. So 10 and 11. So go to over pick and go to pick. Normally, while we go down to pick, we would like to go slower. So let's say 0.3 multiply this, for example. And in this case, if everything is correct, we want to case 11 to reach the pick point and perform the pick operation. So if I want to reach the pick point, I must wait to reach it. And then, for example, I can say that I want to close the claw. Claw close is true. Now, on a real machine, maybe we have some kind of sensor to detect while the claw has taken the product. And maybe also some check to see if we really take the product. Now we do not have, so we just make some timer claw equal to TFB, which is the time variable, the time from begin, and we just say, okay, it's half a second to pick the product. And then we just set it here, timer claw, all right. And then we will go to the next step. I must do a break. I must go to case 12. I must do claw close. And so again we say if the timer is bigger than TFB, break. So we just wait the timer. And that's the point. That's 12. So, all right. If after the timer has passed, we know that the product has really been picked. So first of all, we would like to move back from pick to over pick. Let's say go back. Oh, I'm writing so bad. Go back to over pick. And again, we check. Is it everything good? This is the move number 12. And then, now again, since we have this overlap, we know that while the move will be at 5 millimeters from the point, it will automatically engage the next move if requested, okay? So, in this case, these two moves will be overlapped. But here we wait to reach the point. Precisely because we need to do operation. So to do the operation, we must be in that point. While here we say, okay, go to overpick. Then, for example, we can move. In this case, we move joint to the overplace because the overplace can be very, very far. And we know that from the overpick to the overplace, we should be in the free space. And so we are allowed to move joint. We avoid any kind of problem according to the impossibility of the path, as we said before. Imagine the place point is on the other side of the robot, so it will never go inside its own shaft. And together with this, we will not care about the trajectory because we are in a safe position. So go to overplace in joint mode. So it's always possible, and we will make like a circle, of course. Move here, and again let's pay attention. This will be number 13, correct? Yeah, 11, 12, 13. And finally, if we have other problems, we say nothing, and then from this point we can already go to place. So go to place. Go to place point. Here is a Cartesian movement to P4. That's the move 14. And now that we did all of this, we can go to case 13 and break, of course. Case 13, reach the place point. And here again, here we would like to wait to stop, wait to finish the move, and then okay, that's just some standard stuff. Here we will open the close, of course, sorry, false to the close command. We will set again the timer to give to the close the time to open to the actuator, and then we will go to 14. And 14, of course, will be something like this, while we will move just up. And we will move just up, of course, checking if any problem occurs. So this will be 14, close, go back to over place, which is the P3. If any problem, that's error number 15. And if everything is good, we have to go, I think, we will go to number 1 again. So while the axis will be stopped, so when we reach the over place point, we will be able to begin a new cycle if requested. So in this case, we would like to copy, paste, and go back to 10. Did I say it correctly? No, it was number 1. It was, yeah, number 1. Very well. Now, let's save. And after this, let's also take into account one more opportunity. So first I didn't write the request. Where is number 1? RPE can place. That's again a user request. So that's R1.14. And this is peak and place cycle start. And so here we begin the pick and place. Okay, the other possibility we said could be to do a path. And so here we do a path. Normally the path is some of the most interesting things we do. We can make a path thanks to many ways. We can use some ISO moves. So you can go here to the RPE manual, go back to home, and see the path descriptions through the ISO language. And here we can use something I really love, which is the G-code. So this is what we are going to do now. Otherwise, we can just use some other structures, like let's go back. We can have the other kind of path, the library points, okay, and we can just make something like this, just define some points, some path, and we can use some simple commands like this. You can see the example here and study here to learn something more according to spline or linear. Then we set some speed coefficient like the feed rate, and so on and so on. This is a nice way to describe the paths, but the one that normally on customer side is used is G-code. G-code, as you know, is CNC standard, and so we also use the same way. And now I show to you how to do it. The first thing is to create a path. And so now we just save, we make a new file, and this is our way to write the path. Normally, we begin, for example, with G90, or let's begin with a comment. Comments in our in the NC code we like to use are the same as R3, so are semicolon. So this is sample G code, I say made by Marco Walter. It's 27 November 2023. And now let's say G90, which is the absolute coordinates. Now I'm not explaining so much about the G-code. If you would like to know more, I can make another video for this. Now let's just say we use G90, then we say the F, which is the feed, let's say 20,000, this is the feed, so it's millimeters minute. Let's say that 18,000 is easier to understand because it is 300 millimeters second. And now here we do a G00, which is a fast move, and so we can write. We would like, again, the first move, for example, to be a move to some kind of X, Y, and Z. Let's go to a comfortable place, like here, and then, for example, we would like to stay here, a little higher, okay? Yeah, like this. So it's almost 360. Okay, let's say 700, 450, 360. So 700, 450, 360, and okay, and we also have A, and we say A0. All right. In this case, we will also rotate the J4, of course. Now, after this motion, we would like to, we could do some kind of a function. For example, imagine we have to do some kind of job like a painting machine or like a welding. So we maybe would like to use G82 to open and close the path, to open and close the welder or the paint. I know that in some G-code this could be already a standard command for other kind of things. So if we want, we may just create our own M function like M182, and this could be, for example, a tool open. Then we should check in the task and later also write some piece of code to handle this. So M182, M183, for example, could be some user functions we may use to open and close the welder. Otherwise, in some of our laser machines or glue machines, if you see the Robox standard, normally we use G82 and G83, but as I just said, sometimes they could be used for something else. So I just keep then commented, and it is, for example, open a laser and close the laser. In case, as I said, you find our demo, you will see these kind of things. So after we open this, let's say before this, we also would like another G00. We go down at, so for example, the first could be Z560, and so here we want 360. So we go down, and then, for example, we can use relative coordinates and just say G01, and I want X, for example, 100. Maybe it's too much. Let's say X50. Then G01, Y100, G01, X minus 100, G01, Y minus 100, and finally G01, X X plus 50. Okay, do you understand? In case I begin, it's like beginning a square in the center of one side, and then I say move positive 50, positive 100, then negative x100, negative y100, and again 50 to reach the center. Of course, sometimes these can overlap the begin point, and so maybe going more than 50 in case you want to weld or paint more than the initial point, because sometimes also the open and close of the tool can have some delay, but this is something depending on your machine. Now that's just a sample, so we finish, and then I say okay, M30 or normally M2 is also more standard to say that the path is closed. Again, you can come here and see the standard ones we used, and according to the M and G codes. All the others may be used in some more developed code, like we use the XPL, which is not explained in this lesson, but keep in mind we have more updated things to move in this way. And now, okay, that's an example. Let's save it. And let's call it, this is not a txt file, we would like NC. Actually, we can open any kind of text file, but let's keep some standard. And so this is isosquare.nc. And we save it. All right. Now that we have this isosquare.nc, we can go and okay, let's go here in Flash, and here, for example, we want a user folder, because imagine the end user is making its own path, and we don't want it to make a mess in the FA folder, and of course not even in the FAT. So we create a user folder FB, and we will always tell the customer to only use this. So here we add the file and isosquare.nc, and we load it here. Perfect. So now we can, in order to play it, we can come here, come again to the task, and here, in case we want the path, we need first to call it rpath_start, and here it will be r1.15 gcode path start command. All right, copy, save. Let's go back to case number 1, and we say if we have the path start, we will just go to the, let's say anyway, we will always keep the claw in this point, the claw open, and here in the path start, for example, we would like just to go to another case, and we go, this is case 20, so here we begin with 20, case 20, and this is path file load. So the command we use result is pa load from ISO file. And here we can just copy, come here, check the manual, the grammar of this command. So we have a file name, and then we should have some path variable. We should define it in the task 1. Then we may also have some additional data that we would like to use. Okay, normally we can just use the path and then we can set some important values. So let's say first we need the path. Now let's just say string path is /fb / just. Okay, now in this case we just write it in a simple way, in a direct way. Otherwise we can, of course you can edit some kind, for example, of SR. Okay, no, we do it SR string path, and so this is SR string path. SR, as we know, is here, and it is lit here string, not 10, string 1, path name. So this is, I call it ISO square.nc. Here we load the string and then we say, for example, we need the structure of the path. So this is a ISO buffer, for example, and this ISO buffer is a variable of kind path that we have to declare here at the begin. Very well, that's a path. And so in this ISO buffer we can check some values. First we need to see the PA load from ISO file. Maybe the PA load from ISO file can have some problem, and so if it is 0 it's okay, otherwise problems. So let's say if result is different from 0, and here again we will say we will do the same stuff. Actually this is not a move, is a path, but I don't want to make other alarms, so just call it 99. We will remember that number 99 is the path. And so then here, if everything is correct, we can write some settings in the path structure. So for example, the speed t is the maximum execution speed. So speed t, sorry, this should be okay, system stuff. Speed t, for example, let's say 350.0, and acceleration t could also be some parameter we set. Let's say, okay, 2000. Some other stuff, okay, other stuff, segment number, segment type, so many flags, and so on. Okay, the jerk, the jerk could be used according to each segment. So the segment indexes, okay, range from, okay, we do not care too much. Let's just set these values. If everything is good, so we will execute the path. And so we will do PA path, PA exec path. Oh, sorry. PA exec path. And here, if I remember correctly, I should just set which path, and that's the axis group and the path. Very well. So the robot will execute the ISO buffer. And here again we may check the result. If number 1, it will be the execution has been launched correctly. 0, it's already queued to a previous path because we may load more ones. Never load too many ones in memory at the same time, and never do too big files. And but in this case we just use that one. So we say result, and here again let's say that if different, not different, in this case 1 is allowed, so 1 and 0 are good, negative numbers are bad. So okay, let's call it 98 and 99, just to have some difference. And if everything is correct, we would like to go to the next case. So that's case 21. Case 21 in the path needs to check the path start. It can take some time. So some time according to the system. So some sample intervals, some milliseconds. In this case, we should anyway check it. So if the robot dot vtan, for example, is less than 0.1, we just break. Okay, in this case we know it's moving. As long as the speed is so small, remember that the speed, the vtan, is a tangential speed, so it's always positive value. It's from 0 to infinite. And so it will never be negative, so as long as less than 0.1 means that the robot is not moving. So stop, otherwise we can go to case 22, and case 22 actually will be, no, the case 22 is just to wait to finish, and the case we wait to finish could also be number 1. And so we don't need anything else. Just go to number 1 and do the path. So let's save. This is just a sample. Let's actually it should be better to keep a 22, okay? It's more safe because for example we could have some operations. So now the number 22 is the real this is path execution. So in case we have something we would like to do, we can do here. So here we can do some code for the path execution, like checking if the laser has been started or stopped or something else, operations and so on. And finally we will say if the X is stopped, we will just go back to number 1. So let's copy, and in this case we will go to number 1 and break and if. Very well. This should be the end of everything. Let's save, and now let's make and we play with these new features. Now, in order to play, I need to take out the power, now make, and while we make, I also select FB because I need to load, to create the FB, and to load inside the path. Now confirm, and let's see if compilation is finishing successful. In fact, it's not. Okay, telling me that R status auto was not declared. Okay, it's right. Let's just go here, lit R status auto, and this is, okay, just to say R100, this is automatic state. Let's say automatic status of finite state machine. Very well. Of course, at the beginning of the universe it will be 0 because it's R register, and so R register, our registers are reset to 0 at every boot. And the result was not set, so int result. Now we try again, and we try to make and compile. It's compiling very well. Now it's successful. Let's make some order in these windows. Let's put them around. And now we will soon see something more. Okay, let's do one more thing. While we want to play the pick and place, first we need the buttons, of course, so let's do them. And then we will load a box here in the 3D panel. This could be another interesting tool. We put it monostable, anyway it's not important. And here we make the path start. All right. So that's the first thing we would like. And then I said, let's start and see if it works. Let's play the oscilloscope. It will always be nice to see. Alarm reset, feedback and power. Now we are in number 4, so we do not have the 0 done. We can check it. We can say dv c0 done, which is 0. Okay. Now if I press 0 request, he did it. And so if I check again dv c0 done, I press the arrow up. Pressing arrow up means going back to see the history of commands, so I can call them again. And now it's 0xf. That it's also 15 in decimal, and we know in binary it's 1111, which means 1 bit per each of the 4 axes which already made 0. Very well, now it's execution. Now let's play. And let's, for example, start. We also would like to see the status, and we put it, for example, here. We have some space. Anyway, it's a little number, no need for so much space. Value and status. And of course, the text must be top center. Nice. Status 1. Okay. Let's do a pick and place. Oh, error -8 in move 10. Let's see the error. So if we had this error -8, let's check the manual. So this is the move 10. Move 10 is of course this one, move Cartesian to P1. Okay. Let's see what kind of error generated -8. If the start point is near singularity. Oh, interesting. Yes, of course, I did it wrong. That's due to my initial point. Yeah, I cannot set the home like this. My fault. Of course, since it is a SCARA robot, asking 00 means to have the arm completely open, so completely extended, and that's not a beautiful point. In fact, as we said before, this is exactly the kind of thing that we should never do. Then I know that the speed may be somehow fast, so we reduce it. We make it 0.8. All right. And here also we may modify some points. Okay. And now, for example, let's also do another modification. In case in the mode change, in case we are in power off, let's say that we would like to reset the status of auto. So R status auto, this will go back to 0. And finally, we modify also the P3. Okay, let's put it 150 minus 150. No, sorry, minus. All right. And now let's kill the feedback. Just come here and just do a make. As always, we can check. Okay, it was so fast. It rebooted before we saw messages. But okay, we know it's correct because it completed the make instruction. Now let's clear the shell. Oh, sorry. Or even better, sorry, here I wanted this. Now, let's do again. No, actually it's not important. This could be just QC2. This is something I wanted to do. I was thinking a better number. And now let's go to automatic cycle. Let's play, let's alarm reset, power, and let's start the pick and place. 0. Execution, let's say sum equal to 0 to avoid boring following error system in this game, in this simulation. Now let's do this, and again I have speed 0. Okay, no problem, I can do alarm reset. Robot.runtime, it went down thanks to the hold time, sorry. And now let's make alarm reset, power, and let's start. Sorry, I must say it again. Okay. And pick and place. Let's go up. Let's take, let's move, let's place. Okay, so this is done. Now let's make speed even less, and let's put one more object. So for example, we make a cube and we put it in position as robot.qc1, copy, paste. It's even better to put qt to stay in the tool, qt 1, 2 and 3, and why not also 4. Oops, sorry, this is qt.4. And just to have some offset, let's go back of 50. Yeah, maybe more. Okay, it's too big. Let's take the cube, let's make 100. This should be enough. Okay, now let's do, and let's make it visible only. Here it's not always true, but only when we have the close command. So when we have the rcmd close, I will paste it and come here and play. So if I do again a pick and place, I can take, go up, go down. Okay, here there is a little mistake. We see I made the the motion to go to P1 Cartesian, it could be dangerous. We can see now it's going in this direction. Here is better to move joint. Here, here, here. And we see that the joint movement is very, very, very fast. So now this is something more that we could improve. But together with this, let's also, okay, let's just say while we go to P1, which is here at the end, no, sorry, it's move number 10, yeah, that's not Cartesian, that's joint. And we have seen this motion is very fast, so let's move like this, and let's also reduce in this way. Now this is just a lesson, so it's just an example, but normally we may use different parameter and use a SP0 and SP1, 2, 3 or some other registers to set the correct speed we would like to move. That's because, as we know, Cartesian and joint movement have different parameters and different kinematics. But now, before trying again with this, let's also go to the init. Here, let's say we want sum equal to sum r and are not mask emulation axis. In this way, we avoid alarm 11 to happen in emulation. Okay, so we say that the sum servo alarm mask is equal to the sum itself without the emulated axis. Now, since we already had errors due to the path, let's also check here the ISO position and let's find a better point to begin our path, and let's just say, for example, here we want 400 and yeah, no, let's say, yeah, 500 should be good. Now let's just take out the feedback. Oh yeah, and also in the init let's use small sp0 so we can see better. And now let's make. Now, okay, all of this modification has been done, has been saved, and then together with these modifications we can also try to play the path. Now let's clear the shell. And now the RP2 is booting. I can see the LEDs blinking so much. The watchdog is now on. And okay, we may now connect command, panel, and let's say alarm reset, power 0. And let's now start our pick and place. Okay, yeah, now it's very, very boring. The speed here is very slow. We can increase in this case speed 0x03. Okay, a little better. Now we pick the cube, we go up, we place the cube. Very well. If we ask again, we go down, we pick the cube, go up, over, place, place, and finished. Very nice. Now the last thing we can do is the path. Before it, let's just reduce the speed, because this is also something we are not allowed to do so fast. So let's just make it slower, and now let's just load it in Flash. We can make it runtime, it's not a problem. So load in Flash. Yeah. Okay, now we can just kill this, give it back, give it power. I go to the beginning point. Let's go up and now let's make the path. So I move it here, go down, and okay. Here I have made this square. Let's do it again. Go up, go down, and okay. Now we move it away manually to see the path result. Okay, I go manual, I go up with Z, and so here we can see that we made the square. I can go again manually, I can do once more. It's a tiny square, but we can see that the path has happened. And here we can see the speed. Now I didn't set the jerk, so it's close to infinite, but this is also something we may set, but it's something step by step. Okay, this is almost everything you need to know about RPE. You know the initial informations in order to start developing your own system with robotics. And if you need to know more, you can see further videos, or as always, you can refer to the manual here. And do not forget, here in RDE, in the workspace, you can find the library of examples, and at the end of this there are many ones here which are about the RPE and some of the main machines we may do. Thanks for your attention.